So the next presentation is on artificial recharge mechanisms via a leaky riverbed, a case study in the outskirts of London in the UK. Ilias. No? Oh, there he is. He snuck up with the dark clothes against the dark background.
That's right.
Okay, over to you. Thank you very much.
Thank you. 129, please. Thank you. So I'm going to make it very quick since it's after lunch. I'm going to talk about a case study in the outskirts of London, UK. I work for Affinity Water as a hydrogeologist. Affinity Water is a water supply company in the outskirts of London, supplying water to 3.6 million people. So through this particular case study, I want to focus in this catchment. Just to give you the setting very quickly, we're talking about the chalk aquifer, the chalk being a biogenic limestone. It is unconfined in this part of the catchment. The main characteristics in this map is the confluence of two major rivers, and then flowing down up to the gauging station at the bottom, a number of chalk groundwater abstractions sort of dotted around in those turquoise colors, as well as a sewage works discharging to the river. So what we have here operating is, as I'll show you in a bit, is a complex system with lots of inputs and outputs, but that works quite well. So what we did in this area is we did 2 riverbed leakage assessments. We wanted to understand whether the river is leaking to the aquifer naturally or under abstraction influence, and at what rates, under different hydrological conditions in the background. So this first one was done under high groundwater levels in the background, starting from the right-hand side, upstream, moving to downstream as you move to the left. We see that approximately the river is flattening at the very first 2 kilometers or so, and then there is a variable pattern with some losses and some gains, but approximately up to approximately 10 megaliters, as we see here. Anyway, to the left of the graph, during those conditions are lost to ground, to the aquifer, under high groundwater level conditions. Repeating the same exercise now, but under low groundwater level conditions, similar to a drought, we have an average loss of 6 megaliters a day or so. However, the difference between the previous graph and this graph is that the sewage works is discharging at this time. There is a paradox here. Somebody might think, well, how can it be that a sewage works is not discharging in one occasion and discharging in the other occasion? But actually, in this particular case, the sewerage company abstracts from a trunk sewer and discharges locally. So in the previous graph, it wasn't discharging. In this graph, it is discharging. And we see the huge spike and then the loss between those 2 points. So having studied this and looking at time series and comparing now the upstream gauging station with the green color to the downstream gauging station with the red color, and plotting background groundwater level with the blue color and sewage discharge with the purple color, what we see is that there are times when the sewage works is not discharging. However, the flow is higher downstream, as you would expect naturally from a base flow dominated river, as you compare the green line and the red line, the upstream gauge with the downstream gauge. But there are times when, if we zoom in here, during drought conditions, when the groundwater level in the background continues to decline, we would expect the flows to continue to decline in the same manner. However, at that time, the sewage works kicks in and provides that additional flow to the river. So effectively, the red line equals the purple line, so all the sewage works effluent, treated effluent discharge is found at the downstream gauge. However, the green line shows that the gauged flow upstream of that is lost to ground. So during those drought conditions then, we see that approximately 10 megaliters a day or less is recharging the aquifer and supporting the groundwater abstractions during those times. So just to conclude then, I'm not going to go through all of these, but the main point here is that through this case study, we've studied that the leaky nature of the riverbed under high and low groundwater level conditions. We identified the percentage loss per stretch, per section, between the spot flow measurement points. And if we look at this from a water resources management perspective, then it is already happening in the sense that there is already artificial recharge happening, although unmanaged or not so well managed. But in drought, if we're looking ahead in drought, there are schemes that are under investigation at the moment, whereas, for example, capturing winter flows, storing in an existing disused reservoir, and then releasing at the head of the catchment, and use this leaky nature of the riverbed to recharge the aquifer, and then abstract the water in that percentage that would actually recharge the chalk as groundwater. What that would mean is that there won't be the need for expensive treatment of surface-derived water for that water. Because somebody might say, well, if you've got the water in the reservoir, why don't you treat it straight ahead? The problem is that if you don't have enough storage and the refill capacity is not enough, so the source water is not there, then by doing this, we could negate the need for treating the water as surface water, but using groundwater naturally filtrated instead. So I think I'm going to leave it there. And if there are any questions, I'm happy to take them afterwards. Thank you.
Okay, great. That was 5 minutes, 0.1 seconds. So, great. Thank you very much, Ilias.